A single particle of light is traveling toward you from the heart of a distant star. This is the epic journey of a photon, a story of creation and struggle that connects you directly to the universe's most powerful engines. The starlight you see has traveled for thousands or even millions of years, carrying a message from its violent birth. By the end of this journey, you will understand exactly how a star creates light and how that light fights its way across the cosmos to reach your eyes. We will uncover why a photon's escape from a star takes longer than all of human history, and what happens when light itself gets stretched by the expanding universe. When you look up at the night sky, what story do you think each star is trying to tell? This newborn photon exists as a burst of pure energy, a gamma ray born from the heart of a star. It emerges into a world of unimaginable density, a searing plasma so thick with particles that light cannot travel in a straight line. For our photon, this is not the beginning of a swift journey, but the start of a prison sentence. It is immediately swallowed by the star's own body, absorbed and re-emitted over and over again by the superheated gas. This process is not a simple bounce. Each time the photon is absorbed by an atom, it ceases to exist entirely. Its energy is used to excite that atom, and a moment later, a new, identical photon is emitted in a random, unpredictable direction. This is a random walk of epic proportions, a drunken stagger through an inferno. The photon's initial goal is not to reach the surface, but simply to move outward by a microscopic amount before the process repeats. A single step in this cosmic dance might cover less than a centimeter before the light is swallowed again. This is why a journey that should take mere seconds instead spans millennia. The light is not flying through the star, it is diffusing through it, fighting for every inch of progress against the very substance that created it. How does anything ever find its way out of such a maze? This random walk through the star's heart is a battle against pure chaos. The photon is now trapped within the radiative zone, a region of such staggering density that light cannot simply fly through it. Think of it like being in a crowd so packed that you are constantly jostled, spun around, and pushed in a new direction with every single step you try to take. Forward progress is almost an accident, a statistical miracle born from countless collisions. Each of these interactions is a profound event. The photon does not simply bounce off an electron or ion. It is completely absorbed, vanishing from existence as its energy is taken in. A moment later, that energy is released, and a new, identical photon is born, fired off in a random direction. This process, known as scattering, is the engine of the star's inner glow, but for our photon, it is a prison. The distance it covers between these scatterings is minuscule, often less than a single centimeter. In a star like our Sun, this zone is a few 100,000 kilometers thick. A journey that light could make in a few seconds in empty space instead takes over 100,000 years inside this stellar labyrinth. This meandering path is how the star slowly, patiently, moves its immense energy from the core toward the surface. The photon's struggle is not a flaw, but a feature of how stars work, a testament to the incredible density that keeps them burning for billions of years. But how does this chaotic dance finally end? How does the light find a path to freedom? Finally, after its immense journey through the star's chaotic heart, the photon reaches a new and powerful frontier. It enters the convective zone where the rules of the game change entirely. Here, the light no longer relies solely on its own chaotic, microscopic steps. Instead, it hitches a ride on colossal rivers of plasma, vast currents of material that are themselves on the move. Picture a city with 1,000,000 elevators, each one a massive bubble of superheated gas that buoyantly rises from the depths. The photon is swept up inside one of these bubbles, carried along for the ride. This is not a random walk anymore. It is a grand, slow-motion ascent. The bulk motion of the plasma itself now propels the light upward, drastically cutting down the number of times it needs to be absorbed and re-emitted. This process, convection, is a far more efficient way to move energy toward the surface. You can see the evidence of this on our own sun, where the photosphere is not a smooth surface but a seething, granular texture. Each bright cell in that pattern is the top of one of these rising plasma bubbles, with dark lanes marking where the cooler, spent material sinks back down. Our photon, trapped inside one of these rising granules, is finally getting a direct and powerful boost toward the edge of the star. It is riding a natural elevator, a thermal expressway that brings it ever closer to its ultimate goal. After so long trapped in the maze, the exit is now in sight. But what happens when this elevator reaches the very top floor? What final barrier must the light overcome to achieve its freedom and fly into the void of space? The photon's long confinement ends here at the star's visible skin. This is the photosphere, the boundary where the star's body finally becomes transparent to its own light. After its epic journey, our photon reaches a region where the density of atoms drops so dramatically that the endless cycle of absorption and re-emission finally breaks. It is like a deep sea diver after a long and arduous ascent, suddenly bursting through the water's surface into the open air. The oppressive weight is gone, replaced by a sudden and breathtaking freedom. In this layer, the photon can now travel for kilometers, even hundreds of kilometers, without being swallowed by another atom. The probability of escape, once infinitesimally small, now tips decisively in its favor. This is the surface we see when we look at a star, the source of the light that travels across the cosmos. Every color and every shade in that starlight is a direct message from this very layer, a fingerprint of the star's temperature and the elements present in its outer atmosphere. The photon's escape is not a single dramatic event, but the final, successful roll of cosmic dice after countless failures. It streams outward unimpeded, leaving the seething plasma behind. Its internal struggle is over. Now, a new and equally vast journey begins as this particle of light races into the profound emptiness of interstellar space. Freedom achieved, the photon now races into the great void. Its speed is the ultimate constant of the universe, an unwavering 299,792,458 meters every single second. After its long imprisonment within the star, this straight-line flight feels like pure liberation. The photon travels for years, then centuries, then millennia, a solitary messenger on an endless cosmic highway. The distances it covers are almost impossible to grasp. It could cross our entire solar system in a matter of hours, yet the gap to the next star would take years. The journey to a distant galaxy could consume millions of years of travel time. This is the realm of near-perfect nothingness, a vacuum so profound that the photon might travel for light years without coming close to a single atom. Yet the void is not completely empty. Occasionally, the photon's path takes it through vast, dark clouds of interstellar gas and dust. These are not solid walls, but rather diffuse veils where the photon might finally be absorbed by a lone hydrogen atom or scattered by a tiny grain of cosmic soot, ending its original journey and sending a new one off course. Most often, it slips through these clouds untouched, its straight path a testament to the incredible emptiness of space. All the while, the universe itself is not static. The very fabric of space through which the photon moves is slowly stretching, an expansion that began with the Big Bang and continues to this day. This steady cosmic growth has a subtle but profound effect on the light itself, a change that accumulates over its immense voyage. The photon is not just moving through space, it is racing against the stretching of space itself. What happens to a particle of light when the universe expands around it? The universe itself is stretching as the photon travels, and this cosmic expansion leaves a direct mark on the light. The photon's wavelength, the very definition of its color and energy, is slowly but surely pulled longer. This phenomenon is known as cosmological redshift. Think of the photon as a wave painted on a stretching rubber sheet. As the sheet expands, the wave peaks are pulled farther apart, lengthening the wave and reducing its energy. This is not the light slowing down, it is the very fabric of its road being elongated during its journey. The effect was first confirmed by the astronomer Edwin Hubble, who realized that the light from distant galaxies was systematically shifted toward the red, lower energy end of the spectrum. The farther a photon has to travel, the more time the universe has to stretch around it, and the greater its redshift becomes. This provides astronomers with a cosmic ruler. By measuring how red a galaxy's light appears, we can calculate its immense distance from us. For a photon born as brilliant blue visible light in a far-off galaxy, this stretching can be so extreme that by the time it reaches our telescopes, its energy has dwindled so much that it arrives as an invisible infrared wave or even a radio signal. This universal redshift is a fundamental prediction of the Big Bang theory, a permanent record of the universe's ongoing growth written in the light itself. But even as space stretches, the photon's path is not completely empty. It must now navigate the sparse but tangible material that fills the gaps between the stars. Even in the vast emptiness, the photon is not completely alone. Its path now winds through the interstellar medium, a ghostly haze of gas and dust that fills the space between the stars. This is not a solid wall, but a diffuse cosmic fog, so thin that it makes the best laboratory vacuum on Earth seem dense by comparison. Most of the time, our photon slips through this haze completely untouched, a silent traveler on a clear road. But occasionally, its journey takes it through a denser patch of this mist. Here, it might encounter a rogue atom of hydrogen or a tiny, floating grain of cosmic dust. If the photon's energy is just right, it can be absorbed by one of these atoms. In that instant, the original photon ceases to exist, its energy used to excite the atom. A moment later, that same energy is released as a new photon, but this one is often born with a different color and fired in a random direction. This is the process that creates the beautiful glow of emission nebulae, those vast clouds in space that shine with their own ethereal light. The photon's path can also be subtly altered by dust. These microscopic grains act like tiny obstacles, scattering the light and preferentially filtering out the blue colors, which causes a reddening of the starlight that passes through. Much like our own sun appears redder at sunset when its light passes through more of Earth's atmosphere. The interstellar medium is a complex filter, subtly shaping and coloring the light that travels through it. For astronomers, these very interactions are not just obstacles but vital clues. By analyzing how starlight has been changed, we can map the invisible structure of space itself, determining the composition and density of these vast dark clouds. Yet for every photon that is absorbed or scattered, countless others continue their voyage unimpeded. Their straight-line path, however, is about to face its most dramatic test as they encounter the invisible warps in the cosmos created by gravity itself. Gravity itself can now reach out and twist the photon's path. The very fabric of space, warped by immense objects like galaxies and black holes, acts as a cosmic lens. This is not a force pulling on the light, but the road itself bending beneath its feet. Picture a marble rolling across a taut rubber sheet. If you place a heavy weight on the sheet, it creates a deep depression. The marble will no longer roll in a straight line, but will curve around the weight, following the new contour of the surface. In exactly the same way, a massive object curves the spacetime around it, and the photon, traveling this new geodesic, has its path visibly bent. This phenomenon, predicted by Einstein's theory of general relativity, means that light does not always travel in a perfectly straight line across the cosmos. The consequences are profound. A single, distant galaxy, perfectly aligned behind a closer massive cluster, can appear to us as multiple, distorted images, stretched into brilliant arcs of light known as Einstein rings. This lensing effect can also act as a natural telescope, magnifying the light of objects so faint they would otherwise be invisible, allowing us to see further into the early universe than ever before. Most intriguingly, by mapping how light is distorted, astronomers can trace the presence of matter that emits no light at all, revealing the invisible scaffolding of dark matter that holds the universe together. The photon, once freed from its stellar prison, now dances to the tune of gravity's silent symphony, its path a direct map of the cosmos's hidden mass. But what happens when this long journey finally brings the photon face to face with a world like our own? A planetary encounter presents our photon with several possible fates. Its path might finally intersect with a world, a moon, or another celestial body, ending its solitary voyage across the void. When this happens, the photon faces a simple but final choice. It can be reflected, bouncing off the surface like a rubber ball. It can be absorbed, its energy transferred to the material, warming it ever so slightly. Or in rarer cases, it can be transmitted, passing straight through a thin atmosphere or a cloud of gas. Think of sunlight arriving at Earth. Countless photons are reflected back into space by bright clouds and icy polar caps, which is why our planet looks so brilliantly blue and white from a distance. Others are absorbed by dark oceans and forests, their energy converted into heat that helps to power our world's weather and climate. Only a precious few make it all the way to the ground without being scattered or absorbed, illuminating the landscape below. This interaction is the very basis of vision. The reason we can see the planets in our night sky is not because they generate their own light, but because they are reflecting the sun's photons toward our eyes. Furthermore, when starlight passes through a planet's atmosphere before reaching us, specific colors are absorbed by the gases present, creating a unique barcode of missing wavelengths in the light. Astronomers decode this absorption spectrum to discover what alien air is made of, detecting water vapor, methane, and even potential signs of life light years away. For every photon that meets a planet, however, trillions upon trillions continue their journey untouched. These planetary encounters are mere detours, brief interruptions in an epic voyage that now approaches its final, most intimate stage. After crossing such an immense gulf of space and time, how does this ancient particle of light complete its journey by interacting with the fragile matter of a living world? This fundamental duality defines the photon's very existence. It is both a localized particle and a spread-out wave, a paradox that lies at the heart of quantum mechanics. You cannot describe it fully as one or the other, for its true nature depends entirely on how you choose to observe it. When our photon is traveling through the void, its wave nature is dominant. It propagates as an oscillating electromagnetic field, a ripple in the fabric of spacetime itself. This wave character explains how a single photon can seem to pass through two slits at once in the famous double-slit experiment, interfering with itself to create a pattern of light and dark bands on a detector screen. It is not that the photon splits in two, but that its probability wave travels through both paths, and these possibilities interact to dictate where the photon is most likely to be found. Yet, the moment this photon is detected, its particle nature takes over. It arrives as a single, indivisible packet of energy, striking one specific point on that screen. This is the photoelectric effect in action, where light behaves not as a gentle wave but as a hail of tiny bullets, each one carrying a precise quantum of energy capable of knocking an electron loose from a metal surface. This dual identity is not a flaw in our understanding, but a profound feature of reality. The photon is a quantum chameleon, a particle when it is measured and a wave when it is not. This strange behavior governs every interaction it has, from its creation in a star to its final absorption in an eye or a telescope. Its journey is not just a physical path through space, but a dance of probabilities. So what happens when this dance finally ends, when the wave function collapses and the particle delivers its ancient message? This cycle of absorption and re-emission is the universe's fundamental method of handling light. When a photon is taken in by an atom, it is not merely captured. Its energy is transferred, pushing one of the atom's electrons into a higher, more energetic state. This excited state is unstable, a temporary arrangement that cannot last. Almost immediately, the electron falls back to its original level, and in that act of settling, the atom releases a new photon. This is not the same photon that arrived. The original particle of light has ceased to exist, its identity and journey concluded. In its place, a new one is born, carrying the same total energy, but often fired off in a completely random direction, and sometimes with a slightly different color. Think of it as a cosmic game of hot potato, where the energy packet is passed frantically from one particle to the next, its path and properties shifting with every single handoff. This process is the engine behind some of the most beautiful sights in the cosmos. The ethereal glow of a nebula, for instance, is not simply reflected starlight. It is the visible light created when that nebula's gas absorbs invisible, high-energy ultraviolet photons from nearby stars and re-emits them at lower, visible wavelengths. This fluorescence paints the darkness with color. Alternatively, the photon's energy might not be re-emitted as light at all. It can instead be converted directly into the jiggling motion of atoms, which we experience as heat. This is how sunlight warms the surface of our planet, its energy being absorbed and transformed into thermal motion. The likelihood of any of this happening is a delicate quantum mechanical dance. It depends entirely on the precise energy of the incoming photon and the unique atomic fingerprint of the material it encounters. For the photon, each absorption is a death, and each re-emission is a potential rebirth, sending a new traveler off on an altered path through the cosmos. Yet, even in its death, the photon exerts an influence. Every time a photon is absorbed or reflected, it gives a tiny, microscopic push to the object it strikes. This is the subtle but persistent pressure of light itself. This gentle, persistent push is the force of light itself. Every time a photon is absorbed or reflected, it transfers a tiny amount of its momentum to whatever it strikes. This is radiation pressure, an almost imperceptible nudge from a single particle of light. On the human scale, this force is utterly insignificant. You do not feel sunlight pushing you backward on a bright day. Yet, in the frictionless environment of space, where there is no air resistance to overcome, these tiny pushes can accumulate into a powerful and continuous thrust. The principle is beautifully simple. Picture a vast, ultra-thin sail in the vacuum of space, miles across but lighter than a feather. A stream of photons from the sun, countless trillions of them every second, strikes this mirrored surface. Each impact delivers a minuscule push, much smaller than the weight of a snowflake. But because the photons never stop coming, that push is constant and unrelenting. Over days, months, and years, this gentle pressure steadily accelerates the sail to incredible speeds, enabling spacecraft to journey across the solar system and beyond without a single drop of fuel. This is not science fiction, it is the proven technology of solar sailing, a silent voyage powered by starlight itself. Within stars, this outward push of light is a fundamental force of nature. In the star's intensely hot core, the prodigious outpouring of photons creates a tremendous radiation pressure that helps to support the star's immense weight against its own gravity, preventing a catastrophic collapse. For the most massive and luminous stars, this pressure becomes so powerful that it overcomes gravity entirely in the outer layers, blasting their own atmospheres away in a continuous gale-force stellar wind. This process literally pushes the star's own substance out into space, enriching the cosmos with new elements. Even on a smaller scale, radiation pressure is constantly at work. It helps to push the gossamer tails of comets away from the sun, and it can sweep the finest interstellar dust grains clear out of a young star system, sculpting the cosmic environment one tiny push at a time. The journey of a photon, therefore, is not merely a passive transmission of energy. It is an active force that shapes the motion of matter across the universe. And while its mechanical push is profound, the information it carries is perhaps its most valuable gift. Every photon that reaches us is a cosmic messenger, a tiny vessel of information from the depths of space. Its properties are not random, but a precise record of its origin and its long journey. The color of the light or its wavelength tells a direct story about temperature. A star glowing with a blue-white hue is intensely hot, while a red star is significantly cooler, but the information goes far deeper than simple color. When starlight is spread out into a full spectrum by a prism or a spectrometer, it reveals a unique barcode of dark and bright lines. These lines are the atomic fingerprints of the elements present in the star's outer layers. Each element, like hydrogen, helium, or iron, absorbs and emits light at very specific and unique wavelengths. By reading this barcode, astronomers can determine the exact chemical composition of a star millions of light years away. The light also carries the signature of motion. If a star is moving toward us, its light waves are compressed, shifting the entire spectrum slightly toward the blue. If it is moving away, the light is stretched, shifting it toward the red. This Doppler effect allows us to measure the velocity of stars and galaxies, revealing the rotation of galaxies and the very expansion of the universe itself. Even the orientation of a light wave, its polarization, can reveal the structure of magnetic fields threading through the vast clouds between the stars. The most ancient photons we can detect, the cosmic microwave background, are a faint whisper from the infancy of the universe, a snapshot of a time when it was just a hot, dense plasma. At the other extreme, a single gamma-ray photon can signal the catastrophic death of a massive star in a supernova or the merger of two neutron stars. Our ability to decode these messages has transformed our place in the cosmos. We are no longer just observers of points of light. We are readers of an infinite cosmic library, with each photon a page in a story billions of years old. And as these messengers travel, the universe itself continues to stretch the very fabric of their road, a grand expansion that writes one final, crucial piece of information into the light itself. This relentless stretching of space is known as the Hubble flow, a fundamental current that carries the entire cosmos along with it. For our photon, this means its destination is not a fixed point. The very space between galaxies is continuously growing, stretching the photon's road even as it races down it at the ultimate speed. Think of it as running on a moving walkway that is itself being stretched from the far end. You are sprinting forward, but the finish line is simultaneously being pulled away, making the total journey longer and more arduous than you ever anticipated. The rate of this expansion is measured by the Hubble constant, a single number that tells us how fast the universe is growing for every million light-years of distance. This cosmic growth has a direct and profound consequence for the light itself. As the fabric of space stretches, it pulls the photon's wavelength along with it, systematically draining its energy and shifting its color toward the red. This cosmological redshift is not a result of the source moving away through space, but of the space itself expanding during the photon's multi-billion-year voyage. A photon that began its life as visible starlight can arrive at our telescopes as a faint, low-energy infrared signal, its original message subtly transformed by the journey. This expansion also means that the most distant galaxies we see are actually much farther away now than they were when their light first departed. The photon's travel time is not just a measure of distance, but a record of the universe's entire history of growth. Its journey is a race against the stretching of the very stage on which it performs. But if the photon experiences this vast passage of time, what does time itself mean for a particle that moves at the speed of light? For the photon itself, the entire journey is instantaneous. According to the strange rules of special relativity, a particle moving at the speed of light does not experience the passage of time at all. From the moment it bursts free from the star's surface to the instant it is absorbed in the retina of your eye or the sensor of a telescope, no time elapses from its own perspective. Its birth and its death are not two separate events separated by eons, but a single, unified occurrence. This is a consequence of time dilation taken to its ultimate extreme. As any object approaches the speed of light, its internal clock slows down relative to a stationary observer. For the photon, which travels at that ultimate speed, the clock stops completely. This means that a photon traveling for 10 billion years across the universe and another photon traveling from the screen you are looking at right now to your eye share the exact same subjective experience, a timeless blink of existence. Of course, this is a theoretical perspective, as a photon has no consciousness and cannot have a resting point of view. Yet this thought experiment reveals a breathtaking truth about our universe. The vast cosmic history that unfolds during the photon's flight, the rise and fall of galaxies, the birth of new stars, is all compressed into a single, timeless moment for the light itself. We, anchored in our slower reality, are the ones who must wait eons to receive its message, while for the messenger, the delivery is immediate. This profound disconnect between our experience and the photon's reality underscores the truly bizarre and wonderful nature of Einstein's cosmos. The very fabric of space and time is not a fixed stage, but a flexible medium that warps and twists in ways that defy our everyday intuition. And while every photon shares this timeless quality, the journeys they undertake could not be more different in scale and origin. Our Sun is just one member of a vast and varied stellar family, and the journey of a photon depends entirely on which star it calls home. A tiny, long-lived red dwarf generates photons under far gentler conditions than a colossal blue giant. In that red dwarf, the star is almost entirely convective, with great bubbling currents of plasma reaching from its core nearly to its surface. This means a photon can hitch a ride on a plasma elevator for most of its journey, escaping the stellar interior in a relatively brisk few thousand years. But step into the heart of a massive blue star and the story changes dramatically. Here, the core is a cauldron of unimaginable ferocity, and the surrounding radiative zone is immensely thick and dense. A photon born in this inferno can be trapped for millions of years, fighting through an even more protracted and chaotic random walk before it ever reaches the convective zone near the surface. The starting point for the light itself is also fundamentally different. In the core of a blue supergiant, photons are forged as incredibly energetic gamma rays, while in a cooler red star, they may begin life as lower energy X-rays. This initial birthright of energy dictates how the photon will interact with the cosmos on its long voyage. A high-energy gamma-ray photon from a massive star is more likely to be absorbed and re-emitted by interstellar gas, potentially being downshifted into visible light by the time it reaches us. The beautiful tapestry of colors we see in the night sky, from the ruddy glow of Betelgeuse to the brilliant blue of Rigel, is a direct reflection of these vastly different internal journeys and the unique physical conditions within each star. But as these photons finally stream into space, they encounter another invisible force that can sculpt their very essence. Immense magnetic fields woven through the fabric of space now reach out to guide and polarize the escaping light. Magnetic fields weave an invisible architecture throughout the cosmos, one that can sculpt the very essence of light itself. These fields act like cosmic filters, forcing light waves to vibrate in a single preferred plane. This is polarization, a phenomenon you can witness with polarized sunglasses that cut the blinding glare from a wet road by blocking all light waves, except those oscillating in one specific direction. In space, this alignment happens naturally. When starlight scatters off the elongated grains of interstellar dust, the dust grains, oriented by the weak galactic magnetic field, preferentially emit or scatter light that is polarized. By mapping this polarization across the sky, astronomers can trace the otherwise invisible lines of magnetic force that thread through vast clouds of gas and dust, revealing the hidden skeleton of our galaxy. But magnetism does more than just filter light. It can also generate it in one of the most dramatic processes known. When electrons are accelerated to nearly the speed of light and forced to spiral along magnetic field lines, they emit a brilliant, focused beam of radiation. This is synchrotron radiation, the same principle that powers the light in a particle accelerator on Earth. Across the cosmos, this process creates intense beams of radio waves and X-rays. The lighthouse-like pulses from a spinning neutron star or pulsar are powered by synchrotron radiation. The colossal jets erupting from supermassive black holes at the hearts of active galaxies also blaze with this light, generated by electrons spiraling through magnetic fields trillions of times stronger than Earth. These magnetic phenomena reveal that photons are not merely passive travelers, but can be actively and violently birthed by the interplay of matter and immense magnetic force. Their journey is shaped not just by gravity and collisions, but by this invisible, pervasive influence that can both create light and dictate its very vibration. As we follow a photon's path, we see that its freedom to travel is entirely dependent on the emptiness of its surroundings, a measure known as its mean free path. The mean free path is the photon's measure of freedom, the average distance it can fly before its next collision. This single number captures the stark contrast between the crushing density of a star's heart and the profound emptiness of deep space. Picture a single pedestrian trying to cross a densely packed concert crowd, managing only a few shuffling steps before bumping into another person. Now, imagine that same person alone in an endless desert, able to walk for hundreds of miles without seeing a single soul. That is the journey of our photon. Inside the sun's core, its mean free path is brutally short, often less than a single centimeter. This forces the light into its painfully slow random walk, a journey of countless microscopic steps that takes tens of thousands of years. But once the photon escapes into interstellar space, its mean free path explodes to an almost unimaginable scale. It can now travel for light years, a distance spanning trillions of kilometers without a single interaction. This dramatic shift is the key to understanding radiative transfer, the grand process by which energy carried by light moves through the cosmos. The mean free path dictates everything. It determines how quickly a star can cool itself and how much of its original light is filtered or altered by the material it must pass through on its way to us. It is a statistical fingerprint of the density of the universe at every point along the photon's route. To truly grasp the scale of the photon's voyage, we must now place it within the cosmic distance ladder, the step-by-step method astronomers used to measure the unimaginable voids between the stars. These particles of light become our most reliable cosmic yardsticks. To measure the universe, astronomers rely on a technique called the cosmic distance ladder, and its most crucial rungs are built using photons from special kinds of stars and explosions. These celestial objects are known as standard candles because their true, intrinsic brightness is known. Think of it like this. If you know a lighthouse bulb is 100 watts, you can figure out how far away you are by how dim it appears to you. The farther you sail, the fainter that fixed light becomes, following a precise mathematical rule called the inverse square law. The same principle applies across the cosmos. A Cepheid variable star, for instance, pulses with a rhythm that is directly tied to its true brightness. By measuring the timing of its pulses from the photons we receive, we know exactly how luminous it really is. By comparing that known luminosity to how dim it looks from Earth, we can calculate its distance with remarkable accuracy. This gives us the first solid rung on the ladder, allowing us to measure distances to nearby galaxies. But to reach further out, we need an even brighter beacon. For that, astronomers turn to the catastrophic explosion of a white dwarf star, a Type Ia supernova. These events are so violent and standardized that they all reach roughly the same phenomenal peak brightness, outshining entire galaxies for a brief, brilliant period. The photons from such a supernova are our ultimate standard candle. When we detect them, we know their true brilliance, and their apparent dimness tells us the vast distance to galaxies billions of light years away. Each rung of this ladder, from nearby stars to the farthest reaches of the observable universe, is calibrated by the properties of the photons that reach us. Without these calibrated beams of light, we would have no way to grasp the true scale of the cosmos or to discover the accelerating expansion of the universe itself. The photon is not just a message, it is the very tape measure we use to map the void. Yet, as these yardsticks travel for eons, a question arises about their fundamental nature. Can a photon, this timeless particle, ever truly be destroyed? Its immortality is written into the fundamental laws of physics. A photon is a stable particle, which means it does not decay or diminish with time. It is an eternal traveler, forged in a stellar inferno and destined to journey across the cosmos unless something or someone finally intercepts it. This stability comes from its very nature. The photon is its own antiparticle, and it possesses zero rest mass. There are simply no lighter particles for it to decay into. It is the ultimate endpoint of stability in the particle zoo. While some speculative theories suggest that over timescales so vast they dwarf the current age of the universe, a photon might possibly decay, no experiment has ever detected such an event. For all practical purposes, from our human perspective to the lifetime of galaxies, the photon is immortal. This eternal quality is what allows a particle of light from the first stars to still be traveling today, carrying a pristine message from the dawn of time. It is this guaranteed stability that makes every photon a perfect cosmic courier. But this endless journey is not without cost, for the universe is engaged in a constant and delicate tug of war, and the photon is a key player in its energetic balance. This ancient sea of light represents one of the universe's most significant energy accounts. Across the cosmos, every single photon, from the brilliant flash of a supernova to the faintest whisper from a distant galaxy, contributes to a grand cosmic energy budget. The most substantial contribution comes from the cosmic microwave background, a pervasive glow that fills every cubic centimeter of space. This is the cooled and stretched remnant of the universe's fiery birth, a fossil radiation that carries the unmistakable signature of the Big Bang. In the present era, the energy density of this radiation is incredibly low, vastly outweighed by the mysterious pull of dark energy and the collective mass of all matter. But rewind the clock to the universe's infancy, and the story flips completely. For the first several tens of thousands of years, photons were the dominant force, their intense radiation pressure dictating the expansion rate and sculpting the distribution of matter itself. Alongside this primordial background, newer generations of photons continually add to the balance. The combined starlight from all galaxies, often absorbed by cosmic dust and re-emitted as infrared warmth, creates a diffuse interstellar radiation field that bathes every star system. This ongoing cycle of emission, absorption, and re-emission means the cosmos is constantly shuffling energy, with photons acting as the universal currency. The precise ratio of this energy, from light to matter to dark energy, is what ultimately determines the fate of the entire cosmos, steering it toward endless expansion or a potential future collapse. After shaping the universe on the grandest of scales, this particle of light is now on a final approach to its most intimate destination. The moment of detection is the final, definitive end to the photon's epic voyage. After crossing an unthinkable void, its journey culminates in a sudden and irreversible conversion. In the human eye, a photon entering the pupil can be absorbed by a single molecule of rhodopsin within a rod cell. This absorption event is a quantum mechanical trigger, causing the molecule to change shape and initiating a cascade of chemical signals. These signals, amplified millions of times, race along the optic nerve as an electrical impulse, a coded message that the brain ultimately interprets as a point of light in the darkness. This intimate connection means that when you gaze at a star, you are not just seeing a distant sun, you are physically capturing a particle that has traveled for centuries to deliver its energy directly into your perception, forging a tangible link between the cosmic and the conscious. For a telescope, the process is a technological marvel of the same principle. Incoming photons are gathered by a vast mirror, their paths bent and focused onto an exquisitely sensitive detector, typically a charge-coupled device, or CCD. This silicon chip is a grid of millions of microscopic wells. When a photon strikes one of these pixels, it liberates an electron from the silicon crystal through the photoelectric effect. The number of electrons freed is directly proportional to the number of photons that arrived. By carefully counting these accumulated electrons in each pixel, astronomers can build a precise digital image, a map of light constructed one quantum event at a time. The detector's quantum efficiency, which is the percentage of incoming photons it actually registers, is paramount. A perfect detector would catch every single one, but in reality, even the best instruments miss a few, making every successful detection a precious piece of a cosmic puzzle. This transformation from a timeless traveler to a measurable datum is the foundation of all observational astronomy. It allows us to dissect the light, to break it apart and read the hidden messages encoded within its spectrum. The most revealing of these messages are written in the form of dark and bright lines that stripe the rainbow of starlight. These dark and bright lines are the universe's own barcode system. When you spread starlight into a rainbow using a prism, you do not see a perfectly smooth band of color. Instead, you find a unique pattern of sharp, dark lines slicing across the spectrum, and sometimes brilliant, bright lines standing out against the darkness. Each of these lines is a direct message from a specific atom or molecule that the light encountered on its journey. The physics behind this is a precise quantum mechanical dance. An atom can only exist at specific energy levels, like a ladder where it is forbidden to stand between the rungs. For a photon to be absorbed by an atom, its energy must be exactly right to kick an electron from one rung to a higher one. If the photon's energy is even slightly off, it will pass by the atom completely untouched. When a beam of continuous light passes through a cloud of cooler gas, the atoms in that cloud will greedily snatch only the photons with energies that match their specific quantum transitions. This theft of very specific colors leaves behind a series of dark absorption lines in the spectrum, a perfect fingerprint of the gas cloud's chemical makeup. The same principle works in reverse. When a gas is heated and excited, its electrons are boosted to higher energy rungs. They cannot stay there for long, and when they fall back down, they release their excess energy by emitting a new photon. This new photon has a very specific energy corresponding to the exact difference between the two atomic rungs. This creates a bright emission line at that precise wavelength. So, dark lines tell us what cool gas the light passed through, while bright lines tell us what hot gas is glowing on its own. This simple idea has unlocked the cosmos. It was by analyzing the sun's spectrum that we first discovered helium, an element found in space long before it was isolated on Earth. Every element and molecule has its own unique set of spectral lines, a barcode that is impossible to forge. By reading these barcodes in the light from a distant star, we can determine that its atmosphere is rich in hydrogen, sprinkled with helium, and laced with traces of iron and calcium. We can detect water vapor in the atmosphere of a distant planet or complex organic molecules in a vast interstellar cloud, all from the subtle shadows and glows they imprint upon the light. This interaction is the final, detailed logbook of the photon's journey, recording every significant encounter it had with matter along its path. But what if the information carried by a photon was connected to another, even across the vast emptiness of space? This invisible thread connecting photons is one of the most profound mysteries in all of physics. Two photons can be born from the same quantum event, their fates instantly and permanently intertwined. This is quantum entanglement, a phenomenon so bizarre that Albert Einstein himself was deeply troubled by it, famously dismissing it as spooky action at a distance. Imagine two coins, each flipped in a different galaxy. In our everyday world, the result of one flip would have no bearing on the other. But if those coins were entangled, the moment you saw that your coin landed heads, you would know with absolute certainty that the other coin, an unimaginable distance away, had landed tails. This is not a theoretical guess, it is a guaranteed outcome. The act of measuring one entangled photon, of forcing it to choose a specific polarization, instantly forces its partner to take on the correlated state, no matter if they are a meter apart or a million light-years apart. This connection appears to operate outside the bounds of space and time, suggesting a layer of reality that is deeply and fundamentally interconnected. While this spooky link cannot be used to send messages faster than light, as no useful information is transmitted, it has incredible practical applications. It forms the bedrock of quantum cryptography, where the act of eavesdropping on an entangled photon pair would immediately reveal the intrusion, creating theoretically unbreakable codes. It is also the engine of quantum computers, which use entangled qubits to perform calculations that would take classical computers millennia to solve. This quantum correlation reveals that the journey of a photon is not always a solitary one. Some photons travel the cosmos with a permanent, silent partner, their individual stories forever linked by an invisible bond that defies our classical understanding of reality. This deep interconnectedness, written into the fabric of the quantum world, stands in stark contrast to the very first, simple steps humanity took in using light to understand the cosmos. Galileo's simple glass lenses first captured photons that had traveled unimpeded from Jupiter's moons, shattering the ancient idea of a perfect, immutable celestial sphere. Each leap in our understanding has been built upon a better way to catch and interpret these tiny messengers. When William Herschel discovered infrared light by measuring the heating effect of sunlight beyond the red end of the spectrum, he was learning to read a new page in the photon story, one written in warmth rather than visible color. The true revolution, however, came with the mastery of spectroscopy. By carefully dissecting starlight into its constituent colors, astronomers found those telltale dark lines, the atomic barcodes that finally revealed the sun and stars to be made of the same stuff as Earth. Suddenly, a photon was not just a point of light, but a detailed chemical report from across the light years. This analytical power reached its zenith with Edwin Hubble. By measuring the systematic redshift in the photons from distant galaxies, he saw the signature of cosmic expansion written in their stretched wavelengths. That single observation, drawn from the light of faint, fuzzy nebulae, rewrote our cosmic story, revealing a universe that had a beginning and was dynamically growing. Today, we point telescopes skyward that see in gamma rays, X-rays, and radio waves, each photon from a different violent or subtle process. A single X-ray photon might originate from the searing disk of matter around a black hole, while a radio wave could be the synchrotron whisper of a distant quasar. Every new window we open onto the electromagnetic spectrum is another sense we give ourselves to perceive the cosmos. This entire legacy, from Galileo's first glimpse to the James Webb Space Telescope's deepest fields, rests on the same fundamental event, a photon concluding its epic journey in our detectors. The history of astronomy is the history of learning to listen to the light, and when we consider the immense age of some of these ancient travelers, we begin to see time itself in a new and startling way. Every photon is a time traveler from a distant past. Because light takes time to reach us, we never see the cosmos as it is, only as it was. The starlight from our nearest neighbor, the Alpha Centauri system, shows us a star that existed over 4 years ago. The brilliant light of Betelgeuse in Orion's shoulder departed that star around the time the Roman Empire fell. And when our telescopes capture the faint glow of the Andromeda galaxy, we witness a city of stars as it appeared 2.5 million years in the past. This principle transforms every observation into an archaeological dig. The farther we look, the deeper we peer into cosmic history. The most profound example is the cosmic microwave background. Those photons have been traveling for over 13 billion years, carrying a picture of the universe when it was a mere infant, just 380,000 years old. This is why astronomy is a unique form of time travel. We are chroniclers of ancient events, reading a history book written in light, where every chapter is more distant and more ancient than the last. The photon's journey is a bridge across eons, connecting our present moment to epochs long vanished. But as these ancient messengers race toward us, their path is subtly altered by the most mysterious substance in the universe, an invisible presence that light cannot directly show us, but whose gravity it cannot ignore. Dark matter weaves its influence through the cosmos without ever touching a single photon. This mysterious substance, which makes up the vast majority of the universe's mass, is completely invisible to light. It does not absorb light, it does not reflect it, and it does not emit a single glimmer. Yet its gravitational pull is so immense that it sculpts the very paths that photons travel. Think of it as an invisible mountain range hidden beneath a flat, dark plain. You cannot see the mountains themselves, but you can watch as travelers, their paths bent and distorted, walk in curves around the hidden peaks. In the same way, the gravity of dark matter warps the fabric of spacetime, and light has no choice but to follow these curves. This is gravitational lensing on a cosmic scale. When astronomers look at a vast cluster of galaxies, they sometimes see distant background galaxies stretched into long, faint arcs, like ripples in a pond. Those arcs are not the shape of the galaxies themselves, but the signature of an immense halo of dark matter surrounding the foreground cluster, its gravity acting as a giant cosmic magnifying glass. By meticulously mapping these subtle distortions across the sky, scientists can chart the invisible architecture of dark matter, revealing the hidden skeleton upon which the visible universe is built. This gravitational dance means that a photon's journey is not just a straight line through empty space, but a voyage through an unseen landscape of immense mass, a path dictated by the gravity of something we can never see directly. This hidden scaffold does more than just bend light. It provides the essential gravitational glue that allows the universe itself to take shape. This vast cosmic web is the largest structure we know, a spiderweb of gravity spanning the entire observable universe. Our photon now travels through this grand architecture, a network of immense galaxy clusters connected by wispy filaments of dark matter and gas, all separated by colossal, nearly empty voids. The journey is not uniform. At times, the photon sails through these billion light-year voids, regions of such profound emptiness that its path remains arrow-straight for eons. At other moments, its trajectory takes it skirting the dense edges of a galaxy cluster, or even through one of the diffuse filaments themselves. In these slightly denser regions, the collective gravity of all that unseen dark matter acts like a complex lens, minutely bending the photon's path. We cannot see this bending in a single photon, of course, but by studying the subtle, statistical distortions in the shapes of millions of distant galaxies seen behind the cosmic web, astronomers can map this invisible scaffolding. Each tiny warp in a galaxy's image is a cumulative effect, a whisper of the gravity from all the dark matter the photon passed on its way to us. The light itself becomes a probe, carrying an imprint of every environment it traversed. A photon that passed through a dense cluster might arrive with a slightly different statistical signature than one that traveled mostly through a void. By decoding these faint signals, we can trace the growth of cosmic structure itself, understanding how gravity amplified tiny ripples from the Big Bang into the magnificent web we see today. This intricate dance of light and gravity reveals the hidden skeleton of the cosmos. Yet, on its journey, the photon carries another, more intrinsic property, one that is fundamental to its very identity. Every photon spins, possessing a quantum property known as angular momentum. This quantum spin is a silent, fundamental companion on the photon's journey. Every particle of light carries a tiny, intrinsic rotation, a property known as spin that is locked in at the moment of its creation. Unlike a child's spinning top, which can slow down or speed up, a photon's spin is quantized, meaning it can only exist in one of two possible states. Think of it as a screw that can only be threaded clockwise or counterclockwise. These two states correspond to left-handed and right-handed circular polarization, a fundamental twist in the light's electromagnetic wave. This spin is not just a curious detail, It is a core part of the photon's identity, as essential as its energy and speed. When a photon is absorbed by an atom, it must obey the strict law of conservation of angular momentum. The atom cannot simply take in the photon's energy, it must also account for its spin. This quantum rulebook dictates which atomic transitions are allowed and which are forbidden, governing the very fingerprints we see in a star's spectrum. The manipulation of this spin underpins technologies we use every day. The glasses you wear in a 3D cinema work by filtering light based on its polarization, delivering a slightly different image to each eye to create the illusion of depth. In fiber optic communications, data is encoded by rapidly switching the polarization of laser light, allowing billions of bits of information to race through a glass thread. This quantum twist carried across light years becomes a tool for both nature and humanity, a subtle property that shapes interactions from the atomic scale to the technological. As we consider this spinning messenger, its journey takes on a new dimension, one that is ultimately tied to the grandest story of all, the destiny of the cosmos itself. The universe's expansion is a one-way process with profound consequences for every particle of light. As billions of years stretch into trillions, the relentless growth of space will continue to pull at the fabric of reality, systematically draining the energy from every photon in flight. The brilliant tapestry of galaxies we see today will have long since burned out, their stars extinguished and their stellar furnaces cold. In this far future era, the night sky would appear almost perfectly black to any hypothetical observer. The only ubiquitous light, the cosmic microwave background, will have been stretched so severely that its wavelength will be larger than the visible universe itself, rendering it effectively undetectable, a ghost of a whisper from a fiery past. This is the heat death of the universe, a state of maximum entropy where no energy gradients remain to do work, and no new stars are born to create new photons. The cosmos becomes a vast, dark, and cold cemetery. Yet, even in this ultimate stillness, the ancient photons will not vanish. They will continue their endless travel, but their journey will transform into something profoundly different. These particles of light will become the ultimate fossils, redshifted to energies so infinitesimally low they carry barely a trace of their original power. Their voyages will become immeasurably lonely, spanning an ever more empty cosmos where interactions with matter are vanishingly rare events. The photon's story, which began in a blaze of creation, ends in a whisper of near-nothingness, a testament to the irreversible flow of cosmic time. This long-term destiny forces us to look back at the entire epic from a new vantage point. What does the journey of a photon, from its violent birth to its cold eternity, ultimately tell us about our own place in this grand, unfolding narrative? That faint starlight falling upon your eye is a direct thread connecting you to a distant sun. It is a physical link, a tangible river of energy flowing across the light years, and in that connection, the universe becomes deeply personal. The photons you see are not just points in the sky, they are ancient travelers whose journey began long before human civilization, before the pyramids were built, perhaps even before our own planet had fully formed. To look up at the night sky is to participate in a cosmic event, to complete a story that began in a stellar forged millions of years in the past. This realization bridges the immense gap between the vast, impersonal cosmos and our own fleeting lives. The same physical laws that govern the photon's chaotic escape from a star and its straight-line flight through the void also govern the chemistry of our own bodies. We are not just observers of the cosmos, we are a part of it, made from it. The iron that carries oxygen in your blood was forged in the heart of a massive star that lived and died before our sun was born. The calcium that strengthens your bones was created in that same stellar alchemy. When Carl Sagan said that we are made of star stuff, he was stating a literal, physical truth. The photon's journey is the final step in delivering that inheritance, bringing the energy of creation directly to you. This cosmic perspective transforms our understanding of place. We live on a tiny, fragile world, orbiting an average star in the quiet suburbs of a vast galaxy. Yet, through the simple act of seeing, we can reach out and touch the universe's most powerful engines. The photons that stimulate your retina are carrying out the final command of quantum laws written at the beginning of time, fulfilling a destiny set in motion eons ago. This connection is a profound source of both humility and inspiration. It humbles us by revealing our smallness in space and time, yet it inspires us by showing our deep and permanent kinship with the cosmos. Our curiosity, our drive to understand the light, is the universe becoming aware of itself. The epic journey of a single photon, from its violent birth in a stellar core to its final, intimate interaction with your vision, is one of the greatest stories the universe has to tell. It is a saga of imprisonment and escape, of a straight-line race across an expanding void, and of a message that survives intact for millennia. This particle, born as a torrent of gamma rays, fights its way through a star's dense heart for longer than human history, then bursts free to travel the interstellar highways, braving dust clouds and gravitational curves. Finally, after an eons-long voyage, it arrives as a gentle speck of visible light, a timeless messenger delivering its energy to create a sensation, a thought, a connection. This entire journey, governed by the unbreakable laws of physics, ties us to the grand cosmic narrative, reminding us that to look at the stars is to look at our own deepest origins. This grand journey from a star's heart to your eye is a story written in the laws of physics. We have followed a single particle of light from its violent birth in nuclear fusion, through its chaotic imprisonment in the stellar interior, to its triumphant escape into the void. We have raced with it across the expanding universe, witnessing how gravity bends its path and how cosmic dust colors its message. This entire epic, spanning millions of years, culminates in a single quantum event, a photon delivering its ancient energy to your retina or to the sensor of a telescope. That intimate moment of detection is the final link in a chain of cosmic events, connecting you directly to a distant sun. The next time you gaze at the night sky, remember you are not just looking at points of light. You are completing a story of creation and struggle, welcoming timeless messengers from the depths of space. We would love to hear your thoughts on this incredible cosmic tale in the comments below. If you enjoyed this journey, please subscribe for more explorations into the wonders of the universe. Thank you for traveling with us through light and space.